Yeah, so in today's class, we are going to study this pin diagram of 8086. So on the last turn, we have started 8086 microprocessor, and we saw several points of differences there from 8085, right? 8085 microprocessor is already there, but a need was felt to design some newer architecture so that some of the existing problems could be removed. So the very first thing that we noticed in 8086 microprocessor is that its architecture is divided into two sections. First is called as bus interface unit and the second is called as execution unit. So this bus interface unit is actually responsible for fetching the data from the external memory and generating the addresses for the external memory, because we saw that the addressing is different from 8085, right? And the addressing happened in two levels. If you need to address a memory location, what you need to do is you need to provide the base address and you need to provide the offset from that base, right? You cannot directly provide the 20-bit address in programming, although the address that you provide, which will be of 16 bits for base address and for your offset address, it will be combined by this adder, this additional adder that is attached here into 20-bit address, and accordingly the addresses will be addressed. I mean, memory will be fetched or it will be written by, right? So this instruction queue is also there, which is also different from the instruction register of 8085, because instruction register was a single byte register. Here we had 6 byte register, 6 byte instruction queue, and that is because the longest instruction in 8086 consumes 6 bytes, and most of the instruction they will consume either 2 bytes or 3 bytes. So at a time, more than one instructions can be fetched inside this memory. I mean this instruction queue, and the fetching versus decoding and executing, they remain independent of each other, right? So this is the major point of difference, and this process is called as pipelining. So bus interface unit was mainly involved with these things. And if you see this execution unit, this execution unit is similar to the 8085's architecture, where we have this regular decoding circuit, then timing and control circuit, arithmetic logic unit, which is of 16-bit, and the flag registers. So the flag registers here are 16. So we have seen what additional bits were introduced for flag registers, and this register stack is also present here, which is almost similar to what we had earlier. The only point of difference is this time we had 16-bit registers, and they could also be used as 8-bit registers, higher and lower parts, right? So there are some pointer registers like stack pointer. So this stack pointer will be using the uh, offset address of actually the stack, top of the stack, and it is used in combination with the SS register. This SS register will keep the base address, and this SP register will be keeping the offset address. Similarly, with code segment, we were using this instruction pointer. With code segment, we are using instruction pointer. So the base address will be in code segment and the offset address will be in instruction pointer. With ES, we could use either SI or DI. With ES, we could use either SI or DI, right? So with data segment also, you can either use SI or DI. So this is the architecture of 8086. And as I told you that this architecture diagram, it does not seem complete. Most of the books have this diagram, but as we studied in 8086, there is no representation for interrupts or serial input output data, or maybe the power pins, etc. So in today's class, we are going to study that in totality, and we are going to study this pin diagram, right? So this pin diagram for 8086 CPU is shown on this slide, and you can see that it is still a 40 pin IC, where pin numbers start from 1 to 20, and then in U shape they go from 21 to 40. And the specifications of this IC are that at this pin number 40, which happens to be VCC, you need to supply a 5-volt DC supply, right? A plus 5-volt DC supply, sorry, a plus 5-volt supply needs to be here, DC supply. And it has got, interestingly, two ground pins. This is ground pin number 1 and ground pin number 2. So in one circuit, have you ever seen two grounds together? There are two ground pins in this circuit. So what could be the purpose of keeping two ground pins? Have you ever made a circuit which has two ground pins?
No, sir.
No, sir.
So see, in electronics, what happens is you might have heard the term voltage. So voltage is a relative term, right? You can't say that the voltage of this point is 5 volt, right? You will always say the voltage of this point is 5 volt with respect to some reference, right? Voltage is not an absolute quantity. Voltage is a relative quantity. So this ground pin, it is usually taken as something which has a zero reference voltage, which has a zero voltage, right? It might have some positive or negative voltage depending upon whatever is applied to it. But in reference to this ground pin, the VCC will be having some additional voltage or some lower voltage, which will be called as its voltage. So voltage is a relative term first of all. And whenever you measure voltage between 2 points, suppose there is a resistor which is connected between these 2 points, between this GND and VCC. So the voltage will be measured across that resistor, right? So now in some cases, what happens is when your circuit is big enough, you will say that it also has got 40 pins and 8085 also had 40 pins. But the circuit of 8086 is fairly big enough inside if it comes to the number of transistors that we use. And I have already shown you this when I showed you the history of these microprocessors. The density of these ICs are increasing day by day, right? The number of transistors that it has on this circuit, they increases day by day. So if number of transistors are more, there is a chance that this ground voltage will not remain exactly zero because of the resistor that is connected between these two, or for that matters any electronic component that is connected between these two pins. There will be a similar connection between every other component, every other thing that you see here and this ground pin. So there might be a possibility that this ground voltage will not maintain a zero reference voltage, right? So with the increase in number of transistors, this problem comes. So that is why they have attached two ground pins here, right? So that the load of this will be half and the load of this will be half. So that is why we have got two ground pins here. So the technical specifications of this IC are that it will have a plus 5 volt DC supply here and two ground voltages, right? And unlike in 8085, where we had two inputs for crystal oscillator X1 and X2, here you do not have any inputs for crystal oscillator X1 and X2. Rather, what we have is we do have a clock input. We have a clock input which you can see at this 19th number pin, where you directly attach a clock. And as we have already discussed, the frequency of that clock will be 5 megahertz in the basic version of 8086 CPU, right? So it is higher than the regular operating frequency of 8085, which is 3 megahertz. So you require a clock, you require these voltage of plus 5 volt and these ground connections to be able to start this, right? Now let us discuss other pins, which are again very familiar. So as we said that 8086 is a 16-bit microprocessor. That is why the data bus of 8086 will be of 16 bits and its address bus will be of 20 bits. So its address bus, as you can see from this pin, that is AD0 to AD14, then after that from AD15 to AD19. So from this subscript 0 to subscript 19, we have got a total number of 20 pins, and they are used to transfer the address. They are used to transfer the address there, right? So together with the address bus, we have multiplexed data bus. So 16 bits of that is from 0 to 15, we have multiplexed this with the data bus. So that way we have saved some number of pins, and in the same way the multiplexing was there for your address and data bus in 8085, we also have the multiplexing here, right? So The multiplexed pins, they obviously are bidirectional because they can transfer data or receive data when these pins are functioning as data bus. And the remaining pins, in this case, they are again bidirectional because they can transfer address as well as they can be interpreted as status pins. They can be interpreted as status pins, which we are going to see shortly. What is the meaning of these status pins, etc. So before that, you can also see that I have written here maximum mode and minimum mode. So 8086 is a microprocessor which is designed to work with other microprocessors also, right? So there are some special arrangements in 8086 microprocessor which will tell it that in the circuit there is also another microprocessor, because if you are working in a system and suppose in our college there are two directors, right? So there might be some conflicts at some time, that okay, one director feels that lectures should be of 1 hour duration and the other director feels that no, the lectures should be of 2 hours duration. So there might be some conflicts of power. So this was a problem which was there in 8085 also, that if 8085 has a peripheral and that peripheral happens to be a microprocessor itself, then there will be a conflict between the two in terms of how to control the complete circuit. So in 8086, this problem has been resolved, and they said that 8086 has these pins, and these pins will have one particular meaning when it is operating in minimum mode and another meaning when it is operating in maximum mode. And by minimum mode, we mean that 8086 is the only processor in the system. However, in maximum mode, more than one processors, which may be either 8086 or 8085, 8087, or for that matters, any other processor can be connected. So the pins that you see here, which are written in small bracket, they refer to the minimum mode. And the pins that you see otherwise, they are for maximum mode. So from pin number 31 to pin number 24, we have pins which will have different interpretations under different scenarios. And how are they, how is it distinguished that whether it is working in the minimum mode or maximum mode? So you can see that this pin number 33, it has mn/mx bar. So this is for designating whether this processor is working in maximum mode or minimum mode. So if you apply a 1 here, it will be working in the minimum mode, otherwise it will be working in the maximum mode, right? So the interpretation of these pins will change accordingly, right? So now let me come to the discussion of these status pins, S3 and S4, right? S3 and S4. So this S3 and S4, these are the status pins, and the meaning of this S3 and S4 is this: if the value is 00, it denotes that extra segment from the memory is getting used currently. If the value is 01, you are using the stack segment currently. And if the value happens to be 10, you are using code segment, and for 11, you are using data segment. So these status pins S3 and S4, they are necessary. They are necessary because as we have seen the timing diagrams in 8085's case, so address bus, it usually remains active at the first tick of the clock or the first clock cycle of any instruction cycle, right? So in 8086, we have seen that addressing is at two levels. First of all, we have to provide a base address, and then next we have to provide an offset address. So to be able to tell which segment is getting used, in first clock cycle, you will have address from AD0 to AD19. After this address has been given, when the data segment, when the data bus is getting operational, I mean this AD15 from AD0 to AD15 bits are getting used. Now it should also be known to the processor that with which segment is it working, with which segment is it working, right? So ultimately in that case, what will happen is this S3, S4, these pins will be telling the processor that you have got these meanings, which segment is getting used, right? Similarly, you have got other status pins also. So one of them is S5, S6 and S7. S7 here has got no meaning. S5 is used in conjunction with some interrupts, and here you have again got this S0, S1 and S2 pins. I will make the meaning of them clear, and the remaining pins with the tables when it is appropriately used, right? So these are all status pins, and status pins were also present in your 8085 microprocessor, but they were only two, S0 and S1. and S2 also, 3 pins were there. So accordingly, there was a table and the meaning could be interpreted, right? So status pins are also present here. And after this status pins, I mean, let's take the meaning of another pins also. So after this, we have got this BHE bar. Now, what is the meaning of this BHE bar pin? BHE bar stands for bus high enable. BHE bar stands for bus high enable. Now, bus high enable, as we know that in 8086, the externally interfaced memory, it will consume complete 1 megabyte of locations, or 2 raised to the power of 20 locations. And since 8086 is designed to work with 16 bits at a time, so out of those address locations, 2 raised to the power of 20 locations, every location is of only 1 byte. But 8086, in one go, it can access 2 memory locations, right? And sometimes it will access 2 memory locations, sometimes it might also access 1 byte memory location. So the addresses here are even addresses also and odd addresses also. So sometimes you will be starting with the even addresses, and sometimes you will be starting from the odd addresses to access the 2 memory locations or 1 memory locations. So this bus high enable signal, this bus high enable signal enables the higher order addresses. Bus high enable signals, it is used to enable the higher order addresses or the odd addresses to be able to be accessed. For example, if it wants to access only the higher order byte, so in that case, this BHE bar will be enabled and 1 byte will be accessed. So we will see the meaning of this. I mean, if you see this particular chart, so this bus high enable bar, I mean, this bar is also attached here, but I have used this symbol here to indicate that bus high enable is used in conjunction with this A0 bit. Why? Because if A0 bit is 0, the address happens to be even, or otherwise the address will be odd. This address bus is there from A0 to A19, and this A0 happens to be the least significant bit. So this is the least significant bit. And as you know that in binary number, if the last or the least significant bit happens to be 0, the number is even. So this A0 will signify whether the address that we are using is even or odd. So if it is 0, the address happens to be even, and if it is 1, the address happens to be odd. And this BHE bar, it will also have these values of zeros and 1, right? So let us read the interpretation of this. So if the value of BHE bar is 0, which means the value of BHE is 1. If the value of BHE bar is 0, the meaning of that will be the value of BHE or the bus high enable is 1, and A0 is 0. That means even address is getting used. So even address is getting used, and bus high enable is activated. 0 value for a signal which is having bar will mean that the signal is activated. So bus high enable is activated. So what is the interpretation in this case? Whole word from and to the even address will be used, right? Whole word from and to the even address will be used. So even address, because A0 is 0, so we are trying to read the external memory such that the starting address is even. And since bus high enable is also activated, so lower byte will be anyway read. Lower byte will be always read. But since bus high enable is activated, that means whole word from and to the even address will be read. So the data line that you have got is from D0 to D15. The whole data bus will be there and it will contain certain data. Now, if it is so that bus high enable is activated, but you only have an odd address, So upper byte from and to the odd address will be read. So the only upper byte portion will be read. The bus high enable is activated in this case, but the address happens to be odd. So if the address happens to be odd, then in that case, since you will only be accessing the upper byte from and to the odd address. Similarly, for this case, BHE bar is equal to 1. So BHE will become equal to 0 and the address is even. So in this case, lower byte from and to the even address will be read. And in 1 case, there will be no operation. So you can see that in combination, I mean, this BHE bar and A0 will tell you how many bytes to read and from which address to read. How many bytes to read and from which address You should read them. So both of them, if they are 0, in only that case the word will be read, otherwise bytes will be read, right? So this is because we have got, in the external memory, the addressing happens in two ways. You have to provide the base address as well as you have to provide the offset address. And the second fact is you will be able to read two memory locations at once in the best case in 8086 CPU. Sometimes you will be reading two memory locations at once and sometimes 1 byte per instruction. So for that decoding part, this will be very useful when we will make the hardware circuits where the external things will be connected to this processor, right? So this is the usage of this BHE bar signal, and it is used in conjunction with this AD0 pin or whenever it is acting as address, right? So after that, you already know what is this min-max pin is. Now, reads pin is similar to what we had in 8085. This is active low pin, and if it has a value of 0, that means it is activated and the microprocessor is trying to read the external memory, right, or peripheral, whatever it is attached to. Then before discussing the meaning of these pins, let us come to the meaning of these remaining pins. Reset pin is already known to us. Reset pin, what will it do? It will simply reset the microprocessor. Resetting the microprocessor will mean that everything will start from 0, and this microprocessor, when it is reset, it will begin to execute the instructions from address which is of 5 hexadecimal digits, and the value of that address will be FF0, 4 times F and 0. So whenever you reset this microprocessor, this 8086 is so made that this microprocessor will start executing uh, whatever is written from FF0, right? So from that location, probably the operating system of 8086 is written, or appropriate jump instructions are written, which will jump it to the appropriate line of code which is to be executed when the computer starts, right? So this is something which you need to note, that on reset, the address from which the execution will begin is FFFF0 in hexadecimal, right? Then there is this test pin and ready pin. Now this ready pin is actually used with a slower peripheral. If you have a slower peripheral with your microprocessor, then this slower peripheral, if it is connected, it will not be able to work at the 5 megahertz speed, right? So whenever you want to synchronize a slower peripheral with this faster microprocessor, in that case this ready pin will be used, and they both will be doing synchronization through that. So whenever that external peripheral has some data to transfer, or it wants to ask for certain request, so it will float this ready signal. It will make that signal as an input to this microprocessor, and microprocessor will know that the external peripheral is ready for data transfer, and that way the proper synchronization can be established. Otherwise, what will happen is this microprocessor can just give data at speed of 5 megahertz, and if it will keep on giving the data, the peripheral will not be able to accept the data, and some data might be lost because the speed of this microprocessor is very high. So in that case, for synchronization we use ready pin, right? So this is used for external peripherals which are slow, and this test pin has got a similar purpose, but it is mostly used with other microprocessors. It is mostly used with other microprocessors like 8087. 8087, as I also discussed earlier, it is called as numeric coprocessor. So 8087 is also another microprocessor, and it is used in combination with 8086 CPU for doing some math calculations, right? Now, why we have a dedicated processor for doing some math calculations? The reason for that is very simple. 8086, although it has got a richer instruction set, it has got a richer instruction set as compared to 8085. In 8085, we had 74 instructions, right? In 8086, you will have about 100 instructions here, right? So the combinations that you can make here in 8086 will go something up to 1000. Here you only had combinations up to 243 or 246. So the combinations of those instructions that you can have here is way much. I mean, 1,000 combination, about 1,000 combinations can be made. So, the instruction set of 8086 is very rich, and apart from addition and subtraction, you will also have commands to do multiplication and division, and that too in various ways. So you will have multiplication for maybe signed number or unsigned number. So those basic operations will be handled by 8086 CPU. But the thing is, still these addition, multiplication, division, and subtraction, these are not all operations that we need in today's age. Sometimes we might need to take the value of sine of something or log of something. So for those calculations, you have to write some specific programs in 8086. And for these basic programs, if you will keep on writing some functions or subroutines, then most of the time of 8086 will be gone in doing math calculations. So on that note, we use a coprocessor which is called as 8087, and that is very well equipped to perform these math operations in very limited amount of time. So that coprocessor, if you want to synchronize it with this 8086 well, you have got this test pin. So one might argue that with this ready pin also you can have done the synchronization in a way that you were doing for this slower peripherals. So you could have also done that, but that is not possible. Why? Because processor, it demands power, right? Sometimes it will need to be in power. So there is a conflict of power between processors. So the synchronization between 8086 and 8087 or other processors in the system will be, that is why, used through a separate pin, which is your test pin, right? So this is the story of this test and ready pin and this reset one, right? So now let us move on to other pins. We have already discussed this VCC and all these address lines, BHE bar, and all of these pins. And from bottom we have seen these pins. Now on this side we have discussed these ground pins, these address pins, and then now here the pins that you see here, NMI and INTR. So NMI stands for non-maskable interrupt. NMI stands for non-maskable interrupt. So there we had trap instruction, which was non-maskable. In place of that, you have a NMI instruction here, which is a non-maskable interrupt, and INTR, which is a maskable interrupt. So these two pins are there, and you could use these two pins for making the external interrupts to 8086, right? And we will see how these interrupts are acknowledged in minimum and maximum mode when we will see this INTA bar pin, etc. in combination with these pins. So these non-maskable interrupts and maskable interrupts are there. Only two pins are present for this hardware, right? Now, let us come to this maximum mode and minimum mode of operation, right? So this maximum mode and minimum mode of operation, we already know that in minimum mode of operation, this processor will be working alone. So let us discuss this minimum mode of operation first. In this minimum mode of operation, this hold and HLDA pin, we already are aware of what this hold and HLDA pin is. Can somebody tell me what is the meaning of hold and HLDA pin in 8085? Anyone who can elaborate on hold and HLDA pin? We have also studied them in 8085. No one in the class? Raise your hands if you are still present here. Okay, so only 30 people. So since we haven't seen the hardware usage of that till now, so let me again tell you the meaning of this pin, hold and HLDA. So hold as the name suggests is actually used for holding something. So what do you want to hold here? See, at times it happens that this 8086 CPU, or for that matters any other CPU, is in the circuit, and it has got its internal data bus and the address bus, right? So sometimes to be able to facilitate a faster data transfer, we bypass the microprocessor's internal registers and we only use its data bus to be able to transfer the data, right? So in that case, a hold request will be made by the external peripheral or the processor to be able to access those internal address and data buses. And that way, the data can be transferred without the intervention of microprocessor. Because in 8085, we have seen that if you want to transfer the data from memory to the internal registers of microprocessor and then to the peripheral, you have to use the commands which are like MOV, MVI or LDAX, STAX, and then to be able to give the data to the input output devices, you have to use in and out command, right? So the data from the external world, suppose if it is to be taken from the externally interfaced memory to the microprocessor, and then it should be given to the peripheral. So your internal registers will be involved in that, right? And sometimes it might happen that you have got a faster external device. This usually happens in today's scenario also. Suppose I have a computer which has an older processor, which has got a Pentium series processor, Pentium 1, Pentium 2, 3, and 4. And the USB drives that we use today are USB 3, right? So in that case, or any faster device for that matter can be used. So the USB devices that we are using, they are made according to the current standards. So they are faster as compared to the time when the processor was designed. So in that case, if the CPU is involved in transfer of the data, it is a wastage of CPU's time. It's a good idea for the CPU when it sees a faster device, it should give its data bus, and accordingly the data will be transferred from that data bus to the microprocessor to the other devices directly. So for that purpose, hold request is made, and when the hold request is made, all the pins that you see here are tri-stated. All the pins that you see are tri-stated. That means they will not have a logic value of 0 or a logic value of 1. They will go in high impedance state, because the data bus and the address bus, it has been given to someone else, and whatever data is there, it should not be reflected here, because otherwise it will be like, the data will be leaked from these pins, or the data could be changed from these pins. So whenever the data bus and the address buses, they are given to someone else, in that case these pins are tri-stated. They will have no logic 0 or logic 1 value. Their impedance will be very high. So no voltage logic 0 or 1 can be interpreted. And once that is done, I mean when hold request is made, once that is done, these buses are tri-stated, then this HLDA pin will be held high. And that is 8086 way of acknowledging the fact that the data bus and the address bus have been given to some other device. So for that purpose, we use hold and HLDA command in minimum mode. Then you have write pin, which is similar to read pin. The purpose is opposite. If you want to write something into the external memory, then you have got this write pin. Similarly, you have got this M/IO bar signal. Remember, in 8085, this was IO/M bar, right? IO was first and /M bar was second. So here it has been reversed. In 8086, you have M/IO bar, and this will tell the microprocessor, or this will tell us whether we are dealing with the external memory or input output device, right? So for that purpose this is used. Then this is data receive, transmit or receive, DT/R bar. So T for transmit, R for receive, D for data. So data transmit or receive, right? So ultimately, since you will have any external peripheral or memory element attached to the microprocessor, so whether you are using this memory or input output device will be clear by this, but whether you are transmitting or receiving the data, it will be indicated by this particular pin 27. In minimum mode, its interpretation will be DT/R, data transmit/receive. Similarly, there is a DEN pin which is used as an enable to the external ICs. When you want to transfer the data, that IC has to be activated. So we have seen in the hardware diagrams in 8085 that an activation signal could be made by using the combination of these address lines. So in this case, that can be made by this DEN pin directly. This DEN pin, it will actually be put on the enable signal of the external circuit, and that way your circuit will be enabled and it can be used. So you do not need to make this additional hardware by using AND and OR gates or NOT gates to activate or deactivate a particular circuit, right? So DEN pin is directly there, because if you have a microprocessor, it's a general purpose digital circuit, right? So with microprocessor, even if you need to have some AND OR gates to create another circuit, then it defies the very purpose of having a microprocessor in first place. So they have given this additional pin so that additional hardware component might not be needed for interfacing. ALE, you already are aware of what is the meaning of this address latch enable. Can somebody elaborate on this? What is ALE pin? What is address latch enable? Is Pushparaj Singh, you are raising your hand. Okay, gone. Can somebody tell me what is address latch enable? ALE pin. What was the purpose of ALE in 8085? No one in the class?
Sir, it's like that uh, when there is a positive pulse, ALE is 1, it switches to 1, and when it's not high pulse, it switches to 0. Its function is 0 and 1, and it latches on its
So that is the activation of the pin, but what is the purpose of this ALE? Okay, so I will again tell you what ALE means. See, this ALE pin, its purpose is to, as the name suggests, this ALE pin's purpose is to latch something, address latch enable. And what does it latches? It latches the addresses. Why does it latches addresses? It latches addresses because we know that this address and data bus is multiplexed, right? This address and data bus is multiplexed, and only in the first clock tick of a particular instruction cycle, addresses will be floated onto this address bus. After the first tick of the clock is gone, you go to the second tick, the data bus will take over, and from A0 to A15, you will have this data present here. So in that case, the address will be not available. So in the first tick of the clock only, this ALE pin is set to high, so that there is an external device, external memory chip, which is in this case, in the case of 8086, it will be of 2 bytes, because A0 to A15 is data bus. That means 16 bits or 2 bytes are used for data bus. So in the second tick of the clock, the data bus will take over. So 2 bytes of address will be lost. If 2 bytes of address will be lost, in that case, you need to have at least two external ICs to be able to latch whatever was present on this bus. But we have also seen here that A16 to A19, these pins also have two meanings. They also give status signals and address signals, and they are also bidirectional. So in this case, instead of 2 bytes, you will have something more. Not exactly 3 bytes, but not less than 2 bytes. So since the chips are available in the form of 8 bits or 1 byte only, so 3 additional memory chips have to be used externally, so that this complete address from A0 to A19 is latched in the first cycle, first clock cycle, or first tick of the clock of every instruction. So for that purposes, this ALE pin is used. When this ALE pin is activated, that three additional memories or 3 additional bytes of memories that you have externally to this microprocessor, they are already connected to these address lines, and they will latch that address, and that address can be used further in T2, T3 and T4 and so on cycles of that particular system. So is the purpose of ALE clear to everyone now? Is the purpose of address latch enable clear? Yes or no?
Yes, sir.
Okay, so this is all about this address latch enable pin. Now you again have a pin which is called as INTA bar. So this INTA bar, as the name suggests, it is an acknowledge to the interrupt, which is made at these pins NMI and INTR. So this INTA bar is used in minimum modes, right? So this is the minimum mode. Whatever is written in these small brackets is applicable to the minimum mode of the processor, and minimum mode means whenever only 8086 is operating as the processor of the processor of the complete circuit. Now there are these pins. If you operate this in maximum mode, then the meaning of these pins will change, right? The meaning of these pins will change, and let me start by this RQGT0 and RQGT1. So in similar fashion, we have got hold and hold acknowledge here. The terminology has changed for the case when we are using it in maximum mode. Request and grant. RQ means request, GT means grant. So external device will request something and that request will be granted. So it is indicated on this pin number 31 and 30, and there are two sets of requests which can be made, and like in hold and HLDA, only one time the device can be connected, it can make a hold request and HLDA pin will acknowledge it. However, this request and grant signal, it is for some ticks of the clock. In the beginning ticks of the clock you will make a request, and in the later ticks of the clock you will be granted. So the interpretation of that RQ/GT naught is for 31 pin only, and similarly second set of request can be made here, right? So this is similar to hold and HLDA pin. So and the priority order is the RQ/GT naught will have a higher priority as compared to RQ/GT1, right? So these are two requests which can be made. Then there is a lock pin. Lock pin is used when this processor is performing some critical task and you do not want to give the control of your internal buses of the system to the external device. In that case, you will be locking your internal buses, and you will say that I don't want to give the control of my internal buses to any other system, because in maximum mode this will always happen. If two processors are in the circuit, every processor will have its own ego and they will fight for power, right? So in that case, sometimes this 8086 might want to deny the request for this buses, because when we were talking about minimum mode, in that case there were no other processors in the system. So in that case, even if the 8086 was giving its control of the internal buses to other peripherals, those peripherals will only be requesting a data transfer. But when the control is given to another microprocessor, it might want some more. So to be in the interest of 8086 itself, it is having a lock pin, which when activated will lock the internal buses of the system, right? Now, apart from that, there are these three status pins, S0, S1, and S2. So let's see what is the meaning of these pins. Now, S0, S1, and S2, they are active low pins, so a bar is placed above them, and here also I have indicated by a complement sign. So S0, S1, and S2, the interpretation of this is simply this: if the value of all the three is 0, means all the three are activated, then you have an interrupt acknowledge cycle, right? So you might say that in minimum mode you have this INTA bar pin, which indicates that if an interrupt is made and the interrupt request is accepted, that will be acknowledged on INTA bar. But what is the arrangement in maximum mode? So in maximum mode there is no INTA bar pin. There are these status pins S0, S1, and S2, and for a very specific value, which is 000 at these pins, the interrupt acknowledge, that is INTA bar function, will be performed, right? So this interrupt acknowledge is indicated by this. Similarly, one thing to notice here is that these are only three pins, right? But with these you can make 2 raised to the power of 3, that is a total of 8 combinations. So 3 pins now can have 8 meanings, 8 different meanings depending upon their values. However, if you were using only INTA bar pin as one pin, so one pin only had one meaning there. So This kind of thing is introduced in 8086, where with the combination of bits you can have more meanings than the number of pins. So for 000 it indicates an interrupt acknowledge cycle. For 001 it is a read input output port. We will see what ports are in 8086. Ports are definitely addresses, right? So for 001, we are reading the input output port. For 010, we are writing the input output port. And for 011, the halt operation will be done, because at the end of every program, you have a halt instruction. And how do we know that the computer has come to a halt? So for that, we have this 011, which will be indicated on these status bits. However, in 8085, there was no such arrangement. So it was difficult to see it from the hardware, right? So if it is having a value of 100, then instruction fetch is going on. Instruction fetch is going on. And as we said that in 8086, instruction fetch and decode and execute, they will happen in parallel because of pipelining process. So if the instruction fetch is going on, then we will know it. Together with, in parallel, there might be decoding or executing. So if instruction fetch is going at all, and which will happen in the case when the queue is empty by 2 bytes. So if 2 bytes of the queue are empty, then definitely the instruction fetch operation will happen, not before that. So this will also indicate to us that actually 2 bytes have been emptied from the queue. So instruction fetch operation is used there. And for 101, you are using read memory. 110, you are using write memory. So here we had this write signal here, m/io bar, dt slash r, and den signals. So in this case, these are all indicated by these status bits, right? So now 111 is passing inactive, and when this passing inactive thing is used, this passing inactive is very useful in a lot of operations when a slower peripheral is connected to this 8086 microprocessor. In that case, if the peripheral is not ready to do anything, then what microprocessor will do, it will execute its clock cycle. Suppose instruction is taking only 4 clock cycles, or a machine cycle is taking only 4 clock cycles to get completed, but the peripheral that you have is slower. So in that case, microprocessor will introduce some additional T states, some vacant T states, and it will not do anything in that time till your external peripheral it becomes ready to transfer the data, right? So this is the meaning of these status pins S0, S1, and S2, and you do not need to remember the table that you have here. You can always refer to this table. So cramming this table by heart is not necessary. Whenever you will have problems relating to this status pins, this table will be provided to you with their meanings, right? So this is the meaning of the status pins. Now these two pins are left, QS0 and QS1. So let us see what is QS0 and QS1 pins are doing. So let me first show you again the architecture that we have here. So in this architecture, you can see that there is this instruction queue. So let's discuss something more about this instruction queue. The instruction queue is of 6 bytes on the grounds that the largest instruction in terms of memory in 8086 is of 6 bytes. And this instruction queue, it will be fetching the instructions from the externally interfaced memory to the microprocessor, and this fetching part will be independent of decoding and execution part because of the process of pipelining that we have discussed, right? Now, another important point that we have just seen is if the queue is completely full, there is no problem. If the queue is empty by 1 byte, there is also no problem, no fetching will happen. But the moment the queue has 2 locations which are vacant, if 2 locations become vacant, then the fetching operation will start automatically and happen, independent of the status of what is going inside this execution unit. So this is one fact that we have just seen. And now there are another important things, there are another important events that we need to understand about queue. So first is 00, when the status of this pins QS0 and QS1 is 00, in that case queue is doing no operation, right? That means the queue is completely filled by itself, it is completely full, so it is not doing any operation. If 01 is the status of this QS0 and QS1, then the first byte is getting used, if 1 is the status of the queue, then subsequent byte is getting used. It may be the second, third, or fourth byte, or fifth or sixth even. So subsequent byte is used. So first byte and subsequent byte. These are two different phenomena that we need to have. We will not be interested in which byte of the instruction queue has been used. We will be interested in this fact only, whether first byte has been used or whether subsequent byte has been used, because we said that if 2 bytes from the queue are emptied, then the queue needs to be refilled again. So we will be interested in this phenomena only, and this combination is very special, that 1 0 will indicate that the queue has been emptied. Can you believe that the queue can be emptied while the program is running? If the program starts to run, definitely some bytes will be taken from external memory and put into the queue, right? So the queue will be completely filled by 6 bytes, and the decoding and execution will happen in parallel. So the bytes will be taken from the queue. As soon as the queue gets empty by only 2 bytes, the new bytes will be fetched. So will there be any circumstance while running the program such that the complete queue will be emptied? Can you think of one? Is my question understood?
Yes, sir.
Yes.
So, will there be any situation when the queue will be completely emptied? Okay, think about jump instructions. Suppose in your program there is a jump instruction, right? The queue that you have in this microprocessor, wait, the queue that you have in this microprocessor, it will be fetching the instructions from the externally interfaced memory in sequence, right? Because the program is sequential. So it will be, please switch off your mics. Vaibhav, please switch off your mic.
Yes, sir. 1 minute.
Okay, so the thing is, when we have this queue, it is fetching the instructions from the externally interfaced memory in sequence, right? So if there is a jump instruction, after jump instruction, we break the sequence and we jump to some other location. Or if it is a function call, we will be jumping to some another location in that case also. So what happens is, the suppose this 1 2 byte that is being stored here is for jump instruction, right? And after this jump has been interpreted by this execution unit, it has to jump to certain another memory location. But in sequence, you have fetched these codes 3, 4, and 5, 6 bytes also. So those bytes will not be useful now, because now we need to have a code which is not in sequence. So in that case, the queue has to be completely discarded. The contents of the queue have to be completely discarded, and the queue will become empty in that case, right? So if it becomes empty, that will be indicated by this thing, that is 1 0 whenever it is the status of this QS1 and QS0, it is for queue only. So the queue will be emptied in that particular case. Is it understood by everyone? The queue can be emptied also
Yes,
in
sir.
8086. So this is more or less the illustration of what every pin will be doing in 8086. Some status bits they remain. We will talk about these status bits with suitable examples when we will start coding, and that is not too far. Probably from the next lecture we are going to start the coding of 8086, and that will be interesting as compared to 8085, because we want to dedicate most of the time of our course in 8086 microprocessor. We want to learn it thoroughly together with the interfacing of 8086 with different devices, right? And if we understand this, we will be able to understand any other Intel family microprocessors. So in your laboratory, I will show you the architecture of Pentium 1 to 5, then i3, i7, i5, etc. And you will be happy to note that if you are able to learn 8086 properly, all those architectures can also be tackled, right? So that is why we want to dedicate most of the time here. And the architecture portion and the pin diagram portion is almost clear to all of us. And from the next lecture, we will try to make some very small programs and see the various components of this microprocessor to begin with, like the externally interfaced memory, how to deal with, how to generate addresses. Then we will deal with stack. We will see some programs of flag register. We will see some programs of interrupts, etc. And some function making and jump instructions, how they are different as compared to 8085. Right, and the important part that we want to do here is interfacing of 8086 with various components to constitute a complete microcomputer system. That is what we will focus on more in 8086, because as you told me that in 8086 you are already aware of some of the programming portion. So we will be dedicating good amount of time for programming also, but then our major objective is to be able to assemble a complete microcomputer system for 8086. So that will require an understanding of additional hardware components, right? So that's what we are going to do from the next lectures. So any doubts in the current session? Although these two lectures were highly theoretical, because we can't do anything much about it. Since the information was to be displayed for this architecture and pin diagram, so it's mostly a one-way lecture. But still, if you have some doubts, you might ask. Okay, and regarding the assignment of laboratory, I have already extended the date for it by today night, because some people who were trying to submit it at the very deadline, they missed the deadline and they were not able to submit it. So please respect the deadlines and try to submit your assignment at least 6 hours before, or at least a day before the deadline, because if the deadline ends, then nothing can be done, right? So this time I have extended it. By today you can submit your lab assignments, and so if there are no doubts, I will end the session here.
Sir,
Yeah, tell me.
sir, can you share all the slides which you teach here?
Yeah, I have already shared that complete old recorded video lecture series. In that, all the slides are already there. Or you want these slides to be given to you?
Yes, sir.
Okay, I will just upload all the folders of the slides that I have got. So I will upload them probably by today evening. So all the slides from lecture number 1 till now, I will upload them. Okay.
Okay, sir. Thank you,
Thank
sir.
you, sir.
Okay. Okay.
Thank you, sir.
Thank you, sir.